much, and we will move on then to Claire in our rush through talks. So Claire,
Thanks
please go
all.
ahead.
Can you guys hear me?
Yes.
Great. I want to share with you briefly the way that we've been using Parsl here at the Polar Geospatial Center to advance a project using satellite imagery to map Earth topography in an ongoing fashion for change detection. The digital elevation model, or DEM, initiatives that we work on, we have two polar components, Arctic DEM and REMA, which are the initial ones, and then since I think the last time I presented here at Parsl Fest, we've taken on the rest of the world, because why not take over the world? And essentially the components of these projects are that you take high resolution imagery from satellite shot in stereoscopic mode, so two images of a same place on Earth, and then run them through a terrain extraction algorithm, and from that you can get topography essentially with a timestamp on it, so you can do change detection with these resources. But it is pretty compute intensive, and so leveraging HPC has been critical for the success of the project. But as you can see, each of these individual high resolution images covers only 17 by 17 kilometers or so, and we have the whole Earth to deal with here. So between the three projects, there are a total of 1.5 million of these long elevation model overlaps that need to get processed, and each of those has on average about 10 subcomponents. So that makes for 15,000 actual elevation model extraction tasks, and then another 1.5 million of reassembly tasks. So in this way, this is actually a high throughput problem, but the size of it means that it really can only be addressed on a high performance system. So each of these jobs is something on the order of 1.5 to 10 hours long, each of these tasks. So they're not extremely fast. And if you add up that total, we're talking about millions of compute hours. Parsl is critical, of course. I don't need to teach this audience about the ins and outs of job schedulers and queue limits, but it's pretty clear that 15 million tasks, each submitted as a single job, would quickly cripple a scheduler, get you exiled from HPC systems forever, and would require a great deal of penance to ever get out of jail. And of course, most HPC systems wouldn't even allow that number of jobs in a queue. And so with the limits on the queuing systems, which are there for reasonable reasons to make sure that you don't cripple a scheduler, you simply can't get the throughput that you need doing these small tasks on single node or even 2-node jobs. So what Parsl allows us to do is bundle large sets, like 10,000 tasks, into groups. So that means that you can have 4 20-node jobs running, which ends up better for the scheduler and usually gets higher priority when it comes to leveraging these systems. And unlike some of the more static tools, or the tools that do static task allocation, Parsl is very dynamic. So because of the heterogeneous nature of the run times of these particular tasks, it's really hard for us to predict how long any given one will take. And the dynamic nature of Parsl means that a new task can be allocated when a slot opens up, as opposed to us having to know that up front. At this point, Parsl is used on the HPC system. So the workflow in the simplest form is that the satellites shoot imagery. It comes to us at PGC. We assemble the source data into these regions and globus them to, we're currently working on Frontera at TAC. And then a Parsl process does this set of DM extraction tasks. And once that set of 10,000 tasks is done, the data merging set of tasks takes those results and runs it through another Parsl process. Then when all that's done and validated, the results are globus home to PGC. Now, as you can imagine, that works extremely well, except for each one of these Parsl tasks, at the end of a given process, of a given run, there's always the point at which the reserved nodes, here in blue, are greater than the number of tasks you have still left to run. So that's an inefficiency built into the way that we've set up the system. So what we'd like to do, and what we're working towards at this point, is expanding Parsl to both do the DM extraction and the data merging, but as a single step where the job is a set of several DM extraction tasks, 10 or so, that then turn into a single data merging task. But this is done on a larger scale. And that will make the overall runtime of a given set longer. And so it's critical then to also have the space, also have it in these jobs submitted in a way where there's never a time in the Parsl run where there are not enough tasks to fill up the reserved nodes. And that's where we want to move next after that, which is a more of a queue-driven system where there are always new tasks falling into a pool. And each time Parsl sort of resets and submits a new job to the scheduler, it can refill its pool and never get to the point where there's not enough tasks to run to fill the number of nodes that it has allocated. So many thanks to the Parsl team, especially Yadu, for answering our dumb questions. And I'll take any questions you guys have, which I'm sure are not dumb.
Okay, thanks. Any questions? A couple of us were commenting that we're not sure that we've ever heard globus used as a verb before, so that was kind of interesting.
Yeah. You can verb any word you want.
I guess so.
So what does that look like, Claire, when the data arrives? How quickly is that data arriving? Basically, is it continuous or is it sort of sporadic? Is that like a nightly?
It is continuous, truly continuous. We batch it up into chunks that are nightly. But in terms of each of these steps is done on a sort of an iterative basis, on an as needed basis. So when we need more data to run on Frontera, we will assemble new source data and globus it over. Because there's always new stuff coming in, and it just gets backed up to our tape system and waits in this pool.
And you do that manually, so you basically it builds up a PCG, and then someone goes and actually invokes the globus transfer, and then you go and call a Parsl script on the remote resource.
They're all scripted processes, but they do have a component of human interaction to kick them off and that sort of thing. And that's where I think we have a great deal of opportunity to assemble some of these components into a more integrated workflow.
That's pretty cool. Yeah, I'd love to talk more about it. I didn't realize it was part of a bigger sort of ecosystem of stuff that was going on. Very, very cool.
Okay, well, I'm kind of sorry. Any questions from the audience on Zoom as well? I'm not just paying attention very well.
We're gonna have to force questions soon, people.
I have a question from Zoom.
Yeah,
Wonderful.
please go ahead.
Hi, Claire. My name is Stefan Gary. I love your talk. I thought it was really interesting. You mentioned at the very end that you were basically resetting Parsl to then put more jobs into the pool. How exactly does that look? That sounds really interesting.
We're not actually doing that yet. The goal, though, so the way we run Parsl, because these jobs are restartable, or these tasks, I should say, when I show a graph that shows like a continuous process, that's not actually true. It's probably 6 different sets of jobs all running this, and there's interrupts and restarts, et cetera. And so what our vision is that every time it gets to the end of a job from the scheduler's perspective, instead of restarting with the set of jobs or set of tasks that it thought it had to do originally, it says, okay, wait, there's more. Let me just stop entirely, reset with the things that I had in motion, and now I have a whole new set of things. So it's more of a queue-driven system as opposed to a static set of things to be done. And that's what we're moving towards. But we're definitely not there yet. So more next year.
Thank you.
Okay, anyone else?
Yeah, this is David Adams. I'm going to ask for the same thing in my talk later this afternoon.
Okay,